Hello, hello. I'm super excited to be here. I'm talking about some of my favorite things today. So I'm talking about ABCI++, Celestia, and also just app-specific chains in general. So, yes, and here's my Twitter and my GitHub. You can get a hold of me there. I also have like a repo on my GitHub that contains some of the links for this talk because I think I only have like 20, 25 minutes, so I don't have time to cover everything, so I kind of link things a lot. Crazy things that you can do with ABCI++. So I think first I'm going to talk about what ABCI is, what ABCI++ is. I'm going to talk about how we at Celestia use ABCI++. And then I'm going to talk about some of the other things that you can do with ABCI++. So ABCI is, I think it's literally just stands for Application Blockchain Interface. And that's exactly what it is. It's a way for your application to talk to a blockchain. So it seems it's very simple. It allows for developers to sort of separate things out. You know, I can focus on working on my blockchain, and someone else can focus on building their application, and then those two things can talk to each other. It saves a lot of time for development-wise. But also, an interface is inherently limiting, right? You make a certain set of assumptions when you have an interface, and currently, like the current ABCI, it just makes your application, it essentially assumes that it's a state machine, and that's it. You can't really do anything else. If your application isn't stateful, then it's not really that useful to you. So I even go to the point of saying that ABCI++ is one of the most important advancements in tooling for app-specific chains yet. And I know that's kind of like a slightly hyperbolic, but considering like how limiting the current ABCI is, I feel pretty comfortable saying this. So the ABCI, like I was kind of hinting at, is like the ABCI only does stateful mechanisms, and then ABCI++ also does stateless mechanisms. And doing ABCI effectively just does what smart contracts can do, but ABCI++ is doing what smart contracts could never do. And if you don't mind, I'm going to start a timer and open up my speaker notes. Okay, so ABCI++ effectively just adds a few methods. So the first method at the top is called prepare proposal. And this is what happens when essentially a validator is creating a block. So before with ABCI, you effectively just took all the transactions from the mempool and you just included it in a block and gossiped that block out to the rest of the network. That's as simple as it was. Like there was no callback to your application. Your application had no control over that. Now with prepare proposal, Tendermint or anything that's running your blockchain will essentially call this function, and you can have arbitrary logic before you even gossip the block. So this is an incredibly powerful tool. Same goes for process proposal. Process proposal is when the block is gossiped to you, you effectively can run some arbitrary logic on that proposal block, which again is a super, super powerful tool. You can effectively add block validity rules, arbitrary block validity rules into process proposal. And now we go to extend vote. So this is all sort of going in order in like a typical round of consensus. So then now we go to extend vote. So extend vote is when during consensus you've already agreed upon what will go in the block for that proposal block. And now you decide to vote on something else. So this is when whatever's running your blockchain will call your application and pass it some, and then like essentially tell it, it's like, hey, it's time to vote on this new thing. And again, this can be arbitrary logic. Same goes for verify vote extension. It's like sort of like the sibling method to extend a vote. So now you can verify the vote extension in any way that you want. And then finalize block and commit basically does like almost the rest of what the old ABCI used to do. So Celestia, we have a testnet running right now that uses portions of ABCI++. And we can utilize ABCI++ in such a way that effectively we can take off-the-shelf tooling and create like game-changing technology, which is kind of crazy. It's like this was just an interface change. It's just that powerful of a tool where before we were stuck doing only stateful transitions, and now we can have all of these different tie-ins with our application into consensus. So Celestia is scalable, trust minimized, and modular. So it's scalable in that it has really good, one, it doesn't have a state machine. So like no execution layer. So like what's the most expensive part of running a blockchain? It's running the state database. Well, we have a very, very, very tiny one. So essentially all the money that we would normally spend on a blockchain on running the state machine, we don't. We instead spend that money on bandwidth. Now it's very trust minimized because light clients sample data and then they effectively convince themselves that the data is available. So they're not even really trusting the validator set that the data is available. And then they also do something called just like listening for fraud proofs. And when they listen for fraud proofs and sample for data, essentially they have the full security of a full node, which is kind of crazy. Like this is the game-changing aspect of Celestia. We're able to do this in a trust minimized way, and we're able to make it so that the amount of data that a light client has to download is significantly smaller than whatever the actual block is, however big the actual block is. And it's also fully modular. Like the first title said, it's the first modular blockchain. So it doesn't handle execution. It sort of just lets your blockchain handle it. But since it's so scalable and so trust minimized and so agnostic in how it's built, Celestia sort of just Celestia just lets you build basically whatever you want in this trust minimized way. And we can do these game-changing things because we just use ABCI++ and off-the-shelf tooling, and like effectively, like our engineering team like really isn't that big considering. So yes, scalability without compromising on sovereignty. So this is something that I don't want to spend too much time talking about because we already have a blog post that covers this very, very well. But effectively, you can have something called a sovereign rollup. So we're all Cosmos nerds here. And you can have the sovereignty of a Cosmos chain, but the scalability of a rollup and the security of a rollup as well. So we do this without using any state transitions. There's like one state transition, right? You have to pay for the data that you post, but that's it. So the original ABCI basically wouldn't let us do anything. It wouldn't serve any of the purposes that we actually need it to do. So we had to adopt something new, like we had to use ABCI++. So we have this is our data square. So effectively, we take all of our block data and we organize it in such a way that we can stick it in this first square here, the original transaction data. And then we error share it out, and this is what allows light clients to sample this data. Now, one of the main things that Celestia changes is the data root. So it's effectively just Tendermint, but then we take the data root and we swap it out for a commit to this square. And that's basically like the blockchain part of Celestia. Like the rest of Celestia is a different peer-to-peer network for data availability sampling. But just the blockchain part of Celestia is effectively just this. And again, this is like a very simple thing. It would be really nice if we could just plug directly into Tendermint, make this one single change, and then continue on building other things and having just the security that we would normally get by using something off the shelf like Tendermint, something that's battle tested. So there are some things that light clients need to do with the square that we incorporate into ABCI++. So the first thing that they need to do is we need to create the square, like I was talking about in the first case, is like light clients need to sample this square. So we've created this square, we've error assured the data, that's fine, but we also need to organize the data in such a way that the light clients can prove that their data was actually included in the block. And again, this is something that isn't that difficult if you can have a plug directly into consensus. Yes, so this is kind of like what I was talking about earlier. We have the transactions organized in like one, effectively an index. And the same goes for all the rollup blocks. So the messages, it says like message 1 and then message 2, that's effectively a rollup block. You need the messages to sort of be isolated into their own shares so that you can as a light client, you can easily look and find out that if your data that was actually relevant into your rollup block was included in the Celestia block, because you're already convinced that the data is available. Now you need to know that it's actually included in the block. And in order to do that, you have to like malleate the transaction. So again, with the old ABCI, there was just no way to do this. It wasn't it wasn't possible. You had to have this tie-in before you actually propose a block. You have to be able to basically make this call to the application. So this is basically exactly what we do, right? Like I was talking about before, we have that one method called prepare proposal, and block producers organize the block data during this step. Along with that, though, is that we have validators verify that the data was actually organized in the correct way and that all the rollup block data was actually included in that block. So now there's also an important note that the light clients don't actually have to trust validators to do this. There's fraud proofs, but that's a separate thing. That's kind of important to note. Yes. Now, so that's how Celestia uses ABCI++. And that's how Celestia can, we can utilize Tendermint, we can utilize the SDK using ABCI++. A small team can create like incredibly powerful technology. But like I said, we're like the first team to really use this in a testnet. There's still like a ton more that you can do that other teams have already started working on. So one of the things that is going to get like really crazy with the advent of ABCI or the introduction of ABCI++ is effectively MEV. It's going to be incredibly easy, right, for validators to add their own code before they propose a block. That's literally one of the methods. It's called prepare proposal. It's before you prepare a proposal block or before you actually propose a block, I'm going to call a method. That's like literally giving the validators here's where you add your MEV code. That's literally what it is. So it's going to get really crazy. Now, this gets a little more interesting in a delegated proof of stake situation. But like another interesting thing that you can do is custom mempools. So currently now with the Cosmos SDK and with Tendermint, like the mempool is in Tendermint. This design decision is just so that like application developers don't really have to touch the peer-to-peer part of the code. But if they wanted to, and if they had some very custom needs for the mempool, like I think DYDX mentioned this, is you can take the mempool and you can just stick it in that first method. So every time a validator is going to call prepare proposal, they can just have their own mempool, their own custom mempool, take the transactions from that mempool and stick it in the proposal block, which gets gossiped. And then, let's see, you can also have, like I was getting, I think I briefly mentioned with process proposal, is you can add block validity rules. So you can add extra rules, arbitrary rules on the block, meaning like if you want the transactions to be ordered in a specific way, you can do that. If you want the transactions to be ordered by the amount burned, you can do that. If you want to execute certain types of transactions before other ones, you can do that. And if the block producer doesn't actually do this, then the block's invalid. Full nodes just look at the block. It obviously doesn't follow the rules. We're going to ignore it. It's like, this is like a super, super, super powerful tool. Okay, so immediate execution, one of the things that's kind of troublesome with Tendermint is that it has deferred execution. We don't have to go into that too much now, but effectively, how am I doing on time really quick? I didn't keep track of 10 minutes? Okay, awesome. Okay, so Tendermint uses deferred execution. Deferred execution is a little bit problematic, not only for us to think about, because we normally expect that if a transaction was included in a block, it was executed in that block. That's not the case with Tendermint. It's actually executed in the block afterwards. But it's also important for certain block validity rules. It's like if you change your transactions a little bit, then you kind of need to know that they're executed, that they can be executed in that block in order to add a certain block validity rule. So this is something that you can do with ABCI++, is like with process proposal, you can add your own specific logic. Some of that logic could be executing the entire block in that block instead of waiting until the next block. You can also have malleated transactions. So this is something that Celestia uses. And you can take a user's transaction, and maybe this user's transaction has some metadata. The block proposer takes that transaction, they malleate it, they change it in a way, and then it actually gets included in a block. So this is like a really, really powerful tool. We have to use it in Celestia, but you can also use it for UTXOs, general purpose UTXOs. So I'm not a complete expert on Fuel at all, but they do use certain technology like this malleated transactions to have general purpose UTXOs, which is super, super, super powerful. You can do batching of transactions. There's a huge array of things, and like literally right before this talk, John just explained to me that this is like, you could actually describe most of what ABCI++ can do is malleation of transactions. But this is like just starting to get explored with blockchains. It's super, super powerful, and I'm really looking forward to what people come up with this. But you can have dynamic resource pricing. Okay, so I'm not really sure why you would want to do this, but you could. You could, as you are including transactions in your block, you could execute them, and then you can see, like, maybe you have there wasn't a lot of storage used for that block, so maybe you decrease the price of storage. I don't know. Like, you can really get crazy with the things that you can do with the application logic that you can tie into preparing a block and processing that block. Oh yeah, and now we get on to the vote extension portion. So I think Anoma's doing this. And I know that Osmosis is doing it, and it's mempool privacy. So via this extend vote method and this verify vote method is you can actually have all of the transactions are encrypted when you send them. When the block proposer proposes a block, they include all of the transactions in that block already, but they're still encrypted. And then whenever you move to this extend vote phase, they ask all the validators, who each of which holds some portion of the key, to unencrypt them. And then this is a dramatic oversimplification, but effectively they get unencrypted after or in the next block and executed in the next block, but they've already been agreed upon. So there's no opportunity here to order transactions, which is what MEV is. Penumbra uses this for privacy, and in like a very similar technology, it's like the public key. They sort of have the validators collectively generate a public key, and then they do homomorphic threshold encryption. I'm not an expert on this, but this is like sort of the powerful things that you can start to access with ABCI++. You can have low latency, app-specific, super secure, sovereign oracles, and that is the biggest word salad you will possibly hear today. But it is very important. So oracles are traditionally, like, we're all familiar with like Chainlink and having an oracle in your smart contract. It's not very secure. It's just a multi-sig. It kind of like gives you a headache. It's just, I'm not even sure if it can actually be secured unless it's an app-specific sovereign oracle. Now you can do that. You can vote on arbitrary data. This is kind of like we're starting to get into just like, I hope I'm trying to illustrate to you, like, you can really do some crazy things with this. You can do, yes, optimistic bridges. There's probably something you can do with optimistic bridges here. If you chains that can't use IBC, you could do this with ABCI++. And with rollups, there's nothing stopping you. So this hasn't been implemented yet, but there's nothing stopping you from using a committee that's not in your validator set. So this could be modified in the future to have anyone vote on these things and verify the votes yourself. So again, this is not implemented yet. This is super far speculation, but I think that's it. Yes, before I leave, I have to mention a few things. Celestia, I think I already mentioned that we're the first modular blockchain. We have sovereign rollups. We have an amazing blog post that I encourage all of you to read. That's just at our blog. It's like blog.celestia.org. Celestia enables you to have these rollups, and you don't have to have a validator set. Instead, you just use an API. And then if you are also curious to why Celestia is so awesome in the first place, I would encourage you just to look up Mustafa Al-Bassam. And that's it. We're hiring. Huge shout out to everybody who's put in so much work into ABCI++. It's been a lot. And I know that we're all like a decentralized team, and sometimes we don't all agree on the same things. I just appreciate everybody for giving it our best. And that's it. I don't think I have any time for questions. I'm sorry, but